Hi everyone, today we'll continue our discussion on beam deflections. Before we begin today's topics, let me give you a review of previous lecture as we have done always. So in previous lecture, we tried to define the relationship between elastic curve and its second derivative and the applied moment. Okay, so this is what we have done. So we define radius of a curvature, we define the angle theta, and this indicates dy dx, and this indicates 1 over d square y dx square. Okay, so for small deflection, these assumptions are true, and in ME231 we'll only consider small and linear deflection, and we're not going to consider like a large deflection. So for large deflection, you should take the advanced mechanics course in graduate course. And then, in addition to small deflection approximation, we also considered high aspect ratio condition. So under the high aspect ratio condition, the analysis becomes simple. So under the high aspect ratio condition, we can connect the mx over ei, which is the moment divided by Young's modulus, which is the material property, and I, the moment, which is the geometrical property, with the second derivative of elastic curve. Okay, so this is only true when we have large enough aspect ratio L over D. If L over D becomes small, the contribution from shear force and shear stress and shear strain affect the elastic curve, and because of that we cannot use Euler-Bernoulli beam theory. And Euler-Bernoulli beam theory is simply rewriting the equation into like a second or third and fourth derivative of y. So depending on w or v and m, because they are connected through the derivative relationship, we can write down the exactly same equation in different ways. Okay, and please note that these equations are valid if L over D is larger than 10. And for the special case where L over D is smaller than 10, we're going to visit this problem for energy method chapter. Okay, so after this beam deflection chapter. And then after we learn about the definition of Euler-Bernoulli beam theory and the Euler-Bernoulli equation for beam deflection, we also discussed about how to solve the problem. And the strategy we learned in previous lecture is double integration method. In double integration method, we first obtain the reactions from statics, and after obtaining the reaction, we can obtain the moment diagram or M as function of location X. Then what we do is we integrate twice the equation. Then by applying the boundary condition, we can solve for unknowns C1 and C2 to integration constant. And what are the available boundary conditions? We have 4 different boundary conditions, and please note that we can have information of either y over b, either theta or m. So we can have cantilever beam boundary, we can have simply supported boundary, we can have free boundary, we can have, I don't know how to name this, but we have 4 different boundary conditions. And each boundary condition have different mathematical meaning, but you can see that either y over b or either theta or m is specified. And in addition to this boundary condition, we discussed about the discontinuity when we have a point force or when we have distributed loading, and we're gonna have different analytic expression for left region and right region. In that case, we're gonna have 2 different m as a function of x. Then at the boundary and at this interface, we have to use this condition. Left and right side should have the same deflection y, because we don't want to have disconnected beam. And in addition to y itself, the first derivative should be also equal to each other. If this first derivative is not equal, then you have to worry about infinite second derivative, and second derivative is connected through the moment, but unless moment is infinite, you're not gonna have infinite second derivative, and because of that we can impose this boundary condition to avoid the infinite moment condition. Okay, so these are the summary of previous lecture, and after discussing about these basic theories, we solved some example problems. Okay, so what we're gonna do today is, in continuation of previous lecture, in addition to double integration method, we'll solve the problem using quadruple integration, starting from this. Okay, which you can see that fourth derivative, and from here you need quadruple integration. And after solving quadruple integration, we'll also discuss about statically indeterminate problems.